Alrighty, let us go. Next lecture. So now for something different. Actually, I should make this even more exact. Get rid of that guy. Though we will see Newton's laws for the rest of this course, we're now going to start looking at the world in a slightly different way. So I might call this Act 3 of the course, which is the Great Conservation Laws, where rather than focusing on individual interactions, like a hand pushing a box, gravity pulling an apple, we're going to look a little bit more globally and think about what is going on in a more global sense of the Earth pulling on the apple. Just look at the global overall what is happening between the apple and the Earth. And that there seems to be some sort of exchange going on. The Earth is doing something to the apple which causes the apple to move. Interactions are forces. But we can think a little bit more about, what does, if we had to quantify motion in some way, or the amount of motion that is occurring, how might we do that? But I wanted to quickly just bring an end to the Newton's Law section. Overall, everyone should be doing more problems than what we are doing in class. We already are doing more in class than what I've done in the past because we have the in-class sessions. But that doesn't mean you shouldn't be using your book, beyond just the expert TA problems, to think about how to set up and solve Newton's law problems. And if you're going to memorize anything, don't memorize individual instances of how you use Newton's laws, because then you run the risk of thinking, for example, say that every time I see a ramp, I do this. Every time I see a spring, I do this. Which can lead to some problems because then that results in you doing things like thinking the normal force is always mg. Wrong. Right? Writing down that friction is always a fixed value of mu times the normal force. Wrong. Instead, memorize an approach of how you solve these sorts of problems and then reuse that approach to solve any sort of problem that is thrown at you. So here would be my approach. First step, draw a picture. In that picture, identify your system, and with your system, identify the forces acting on the system. That is the force diagram. Translate that into a free body diagram, where the system is replaced by a point, and all the vector forces emerge out of the point that allows you to determine the directions of these forces. Give those vectors names. Write down symbols that correspond to those vectors. Some of them might have components that you already know and can calculate. For example, if it's gravity. Based on the coordinate system, chances are that you're going to have the first coordinate be 0 and the second coordinate be either plus or minus mg, depending on what you choose to be up or positive or negative. So those you might be able to calculate right away. There are some forces that are variable. The normal force, the friction force, they can take on a range of values, and it usually depends on the problem to know exactly what its value is. So if you don't know what the value is, maybe you give it a symbol. If you really like to call something the normal force, maybe it's capital N is the symbol you give it. Once you've identified all the vectors that make up the forces in your problem, identify Newton's third law pairs. If you have multiple systems, that might be the case that there are forces that are Newton's third law pairs between the systems. If you only have one system, skip the step. You cannot have Newton's third law pairs acting on the same system. If that were the case, they're going to cancel each other out. Those have to be forces inside the system, not acting on the system. Then I would ask, is there acceleration? More or less, you're saying, is A equal to 0 or not in each dimension? Cases where it might equal 0. In the vertical direction, a box sliding across the surface. the vertical direction, usually the acceleration is 0, because the box is not floating into the air or sinking into the ground. If there is no change in motion in a particular dimension, that means the acceleration is 0. Be it the velocity is a constant or the velocity is 0. Like, for example, an object that's stationary. Knowing that, write down Newton's second law for each system. For each system, which, since Newton's second law is a vector equation, also includes you writing it down for every dimension for each system. All the horizontal forces must add together to equal the mass times the horizontal acceleration. All the vertical forces must add together to equal the mass times the vertical acceleration. And then algebra to get you to your final answer. In the force section, we saw a couple of forces. Now, all forces can be thought of as pushes or pulls, and all of them, except gravity in this course, are contact forces. There has to be a point of contact between the agent and the system, gravity being the one exception for this class. The long-range force of gravity has a certain form near the surface of the Earth. We will learn a more general form when we do gravity later on near the end of the semester. But when you are close to the surface of the Earth, you can write the force due to gravity as the mass of the object times little g, or 9.8 meters per second squared. Always keep little g as a positive number, positive 9.8. But you can throw a plus or a minus sign in front of this entire expression, depending on which way the vector is pointing in your coordinate system. And to remember this symbol is the symbol for the Earth. So near the surface of the Earth, this is true, where g is 9.8. A particular force we see a lot is a contact force between a surface, sometimes called the normal force. Things to remember about it that are always true. It always points away from the surface. So in other words, it's always perpendicular to the surface. Or normal. Normal being the mathematical fancy term for perpendicular. The normal force is one of these forces that's variable. There is no equation that always works. It takes on whatever value is needed to make the acceleration 0 in that direction. Typically, the normal force means there's a contact force, and most often we see it in the context of, say, a box is on a surface, the surface is pushing up on the box, gravity is pulling down on the box. Clearly, the box is not floating into the air or sinking into the ground, so that means whatever is going on in the vertical direction, the sum of those forces have to equal 0. Usually that involves a contact force or a normal force. So usually by saying the box doesn't leave the ground, you are saying the normal force has a certain value, whatever is necessary to make the acceleration 0 in the vertical direction. I like to think of it as the bathroom scale force. It is the number that would be read if you were to place a bathroom scale underneath the object, which again is not always mg. For example, there is a normal force when I push against the wall. I'm pushing horizontally against the wall. That has nothing to do with gravity. There's still a normal force from the wall. I gave the example where you could stand on a bathroom scale, but then someone else could push down on your shoulders. The bathroom scale number would read even larger than your weight. It is not always mg. If you include the normal force, and you go through the math, and you're convinced that you're doing it correctly and carefully, and you actually find that the normal component is 0 or negative at the end of the day, what that means is you've reached a contradiction. What that means is in the setup you've just done, the box or the object or whatever it is has actually lost contact with the surface. The contact force going to 0, or negative, whatever that means that the object is no longer in contact with the surface. That might be the criteria for when does the object slip off the surface. Or I have a box on a table, and I slowly but surely keep tying helium balloons to the box. Eventually, the box will start to float. Mathematically, I could say it will start to float when the normal force, the contact force between the table and the box, vanishes. We saw the spring force, and we'll see that again when we do oscillations, which is negative some constant times what I call delta S. The negative here has nothing to do with your coordinate system. It just says that it points in the opposite direction as how the spring changes. If the spring gets longer, the force is going to point in the opposite direction because it wants the spring to go back to its normal length. If the spring gets compressed, the spring force is going to point in the opposite direction because it wants the spring to stretch back out again. We saw tension, which for idealized wires or strings, we can treat as a force that is uniform throughout the wire. It's equal and opposite, pointing in both directions along the wire with some equal constant value, except at the endpoints where the symmetry is broken. So if you have two boxes attached to a string that is kept taut, the string has a tension throughout, but only at the endpoints is that tension force being exerted on other objects, so they feel that tension force only in one direction. That is a useful way to have forces, say, change directions. Say if you have a rope across a pulley. Friction can either be static, when there is no motion, or kinetic, where there is motion. Apparently my recording software wants me to upgrade. Not today. Friction always points in the opposite direction of motion, if there is motion, or what the motion would be if the object were to start moving. So in the case of static friction, if you have an object on a ramp and the ramp has some incline, the object wants to move down the ramp from gravity, but friction is stopping it. It's opposing the want to be motion, which is why friction then points up the ramp in that case. This is parallel to the surface. The normal force is always perpendicular to the surface. Friction is always parallel to the surface. The static friction force is another one of these variable forces. Static friction implies that nothing is moving. So it takes on whatever value you need so that the acceleration is 0. So it can be 0 up to some, they can have an arbitrary number of kinds of different values. But there's a maximum value that is allowed. If static friction exceeds some constant mu sub s times the contact force with the surface that is rough and has friction. Again, call it a normal force if you want, but all the rules that we just talked about with the normal force still apply. If the force you've calculated previously exceeds this value, then the object actually is moving, not stationary. Then you need to go back, do the problem again, but now you can't set a equal to 0. There is an acceleration. And the friction in that case is then becomes kinetic friction, where it is the same formula except a different coefficient out in front, a coefficient that is smaller when there is kinetic motion. We've looked at ramps, which are really nothing beyond just an exercise in geometry. If there's an object at some angle, often there will be some force that points not along either one of the axes that I've drawn in green. And the trick there is just identifying the relevant triangle and knowing that whatever side of the triangle is at the adjacent side, that's where the cosine goes. And whatever side is opposite is where the sine goes. Don't always assume horizontal means cosine, vertical means sine, because that's wrong. And we saw that with ramps. The vertical component of gravity is the one that had the cosine. just by the way that the triangles were arranged. And then in general, what happens is that you'll have various different kinds of Newton's law problems that you have to solve. Many of them that we've been playing around with are static situations where nothing is moving. The velocity is zero, which also implies that the acceleration is zero. If that's true, F equals ma, the a is zero. The sum of the forces must add up to zero, e.g. a box staying still on the ground. Though by Newton's first law, that's actually no different than if the object was moving at a constant velocity. Your car is coasting at a constant speed. There are no forces necessary to keep the car going at a constant speed. A better example would be like an ice skater. You push off from the side of an ice rink and you just coast at a constant speed until you hit another ice skater or wall. Nothing is necessary to keep you moving at a constant speed. Another example would be, say you're taking an elevator. You feel that jolt at the beginning, that's an acceleration, but then it feels perfectly fine, and then you feel a jolt at the end. During that middle part, the elevator is traveling at a constant speed. You don't perceive anything during that middle part of the journey. Similarly, like taking a train. If you're in a train and the train is going at 150 miles per hour, and it's a nice smooth track, you can get up and walk around in the car. You can do other things while you're in the train, and you don't feel yourself moving at 150 miles per hour. You feel the accelerations. You feel the bumps and the jiggles and the interruptions. Turbulence on an airplane. You feel that because you're feeling accelerations. The speed of the plane is changing. When things are smooth, everything in the airplane, you could throw apples into the air and you would always catch them. Everything is fine. And then when there's a force imbalance, of course, that means there is a net acceleration. Then the sum of the forces equals the mass times that net resulted in acceleration, like a box sliding down a ramp. I guess, unless, say, maybe there's friction on the ramp. Maybe then the box slides down at a constant velocity. That's a good exam question. What amount of kinetic friction is necessary to keep a box sliding down at a given incline? And so with these strategies, you should be able to approach any sort of Newton's law problem, even ones we haven't seen. For example, we have not done really anything with pulleys in this class, though you might have seen them maybe in high school. But there's nothing I need to teach you about pulleys beyond the strategy I just talked about on the previous page. A question that one could ask is, you have some person pulling down on a rope which is attached to a pulley system. How much force is necessary to make that box lift into the air? Realizing one of these pulleys doesn't have an anchor. There we go. Now, if you start Googling pulleys, no. We know everything we need to know about how to analyze this sort of situation. I would start, of course, by drawing my system. I am analyzing kind of the box that's attached to a pulley. I would identify that there is some contact forces. I see two ropes touching the circle I just drew. I also see the ground that's being touched, and then of course there's gravity. I would say gravity is pulling down. The floor is pointing up. I'll call it normal to appease all y'all. And then there are two ropes as well. There's T left and T right. That is also touching the surface. You might think it's the same rope, but the point is that you look for things that touch your system. Since the rope touches the system twice, we have to include both of those contacts. There are two contact forces as a result. And I might define up as positive. I could define right as positive 2, but this clearly looks like a 1D problem. Then I would say, are there any Newton third law pairs? Or results of Newton's third law. And we talked about how Newton's third law is really the argument why the tension is uniform. So I would say T sub r equals TL in this case. In this case, both in direction and in magnitude, because it flipped around. So since the tension is uniform, I can treat both of those forces as being the same magnitude, in this case also the same direction. I can also look at this problem and ask, what else do I know? We are looking for when the box is leaving the ground. And for it to leave the ground, I just talked about, to leave the ground implies that the contact force goes to 0. So I actually can say something about the contact force. If it's just about to lose contact with the ground, then that contact force must be vanishing. And then, of course, there is gravity. And I think that's it for the system. This person is also in contact with the rope. There, the free body diagram of the rope is that there's a force pulling down on the rope, and there's a tension that is pulling up on the rope. And that tension is the same tension as is over on the other side. The tension is uniform throughout. And this is an idealized system, so the mass of the rope is treated as very, very small, or 0. Now, Newton's second law says this. In general, for the rope, I can write this as the sum of the forces equals the mass of the rope times the acceleration of the rope. But the mass of the rope is essentially nothing, so that's 0. So if up is positive, I might say that this is, well, I'll do it more general. So there's T plus the force of the pull equals 0 as vectors, but then taking into account magnitudes, since one points down, one points up, this then of course implies that T is just the same as the force of your pull. Your pull is creating a tension in the rope. I could then look at the box and ask what's going on with the box. Now, I guess I didn't really state if the box was accelerating into the air, or we could take the case where maybe the box was just lifting into the air at a constant velocity. So I might approximate the right-hand side as 0 again. If there's no acceleration, it's just at a constant velocity the box is rising. We wrote down that this is 2t plus, there's the normal force, which actually is 0, and then gravity. Those were the 3 forces, correct? Yes. Yeah, and there were 2 tensions, which is why I wrote 2t. And then by leaving the surface, we said this is 0. So then 2t minus mg equals 0. But t was the same as f, so 2f minus mg equals 0. Or f equals mg over 2. In order to lift the box off the ground at a constant speed, you need to apply a force that is at least, that in this case is equal to half the weight. This is an example of mechanical advantage for the engineers. Why pulley systems, you can have the rope do double work, in a sense. So the rope is kind of acting on the box twice, which as a result means that you only have to lift with half the force to get the box off the ground. And if you look around, you can find, various contraptions of many, many pulleys and whatnot, so that you have to exert less effort on your end in order to lift a heavy object. Yeah, so if you ever have to lift something, and then we saw this as well, this essentially was the same idea with the boson chair that I did in the optional lecture. So again, there's a systematic approach for these problems. And if you think about the systematic approach, that is what's going to help you. Not memorizing individual examples that you try to regurgitate. All right. We're going to start now by talking about, that we won't talk about it all today. Really where we're going now is energy. And conservation. Both words that have common parlance meanings. So we have to be careful to make sure we are meaning them in the physics sense for this course. Conservation could mean, when you talk about conservation of a forest, for example, that is being used in a way that might be slightly different than what we mean in physics. If you mean keeping the forest the same, that's conservation like in physics. If you mean planting new trees to make new forest, that is not conservation, as we mean it in physics. Also, in physics, the idea behind energy, a broad, very broad definition of energy might be something like a quantity of the system that changes when forces make the object move. If forces cause motion, we will learn that changes this thing we're going to call energy. Forces can act on an object and sometimes not cause the object to move. Just holding up this apple, gravity's pulling down on the apple, but the apple's not moving. So in that case, we will learn actually that the gravitational force in this case is not changing the energy of the system. Or to tease the words we'll be using, the gravitational force in this case is doing no work on the apple. Energy has to do entirely with things that are in motion, velocities that are non-zero. And what is really profound about this thing we're going to call energy is that under certain conditions, it is conserved. In that there can be a certain amount of it that never changes no matter what is going on in the system. Let me give an example of that. Let me give a couple examples actually. I can take a simple example. I can take a simple example where, suppose I have a couple members of the class. I'm biased towards those of us that start with an A. So I have Aaron, Acacia, Alejandro, and Ariana. And that forms the class. And suppose some of us come to class with money. So each of these little things is going to represent, a coin. So I come with 4 coins that I've colored red. Acacia comes with 4 black coins. Ariana comes with 4 white coins. Alejandro came with nothing. At the beginning of class, I could ask, how much total currency is there in the class? And we could say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So at the start, I'd say 12 coins. At the start of class. Now class gets started. We're in class. No one is entering or leaving the class. And we might be doing stuff where we might ask each other to do services for one another in exchange for, say, money. Maybe we're working on a problem set, and it turns out that Alejandro is really good at the problem sets. So Acacia says, hey, Alejandro, how about you do my problem set too? And he says, okay, for 2 coins, I will. And so then he does that service for Acacia. Now he gets 2 of her coins. Ariana gets word of this and says, oh, great idea. I'll give you also 2 coins as well. And so after a while now, this is the state of the currency in the class. Maybe now this is, let's say this is 10 minutes in. 10 minutes in, I could stop and say how much currency is in the class. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 coins. The total amount of currency has changed. The total amount of currency has been conserved, though it has changed hands a little bit. Ariana and Acacia gave some to Alejandro, for example. Then I could let some more time pass in class. There could be a new activity could be up, and it turns out that Acacia is really good at the problems that the students are now working on. So Alejandro and Ariana might be like, all right, I'll give you some money if you help me on this particular problem. And Acacia might do that, and she might get an answer and help them get answers. So now 20 minutes in. I could say, what is the total currency of the class? And we would again say 12 coins. The total amount of currency has not changed. Though again, it is now in a different shape than it was 10 minutes in, which is again a different shape. The total amount is the same, but it's in different hands now after 20 minutes in. And we could keep going. At 30 minutes in, you can imagine where we're going with this. No matter what happens inside the class, it always seems that no matter who's holding on to the money, there are 12 coins total. In this, we would say that the currency is conserved in the class. No matter what shape the currency takes, there are 12 coins. Even when sometimes, it can, things can change shape. For example, I could, turn to Einstein and say, hey, do you have anything you want to sell me? And Einstein might say, should have got another magnet toy. He's like, yes, I have this little globe that I will sell you for 2 coins. So I could say, okay. So I could give him 2 coins, and now I have property of this little globe. And I could then ask how much total currency exists. And in this case, we might say there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 coins, but then I also now have some property that's worth 2 coins. So the total currency in the class is still 12 coins, even though some of it might have exchanged hands, like maybe now Ariana got her money back, or something like that. And so the coins might be in different hands, and now the coins have taken two of the coins took a slightly different shape with this property that I now own. As an example, again, of how things could be conserved. Let me give another example. Let's also use a money example still. we could consider your own personal wealth. Your personal wealth, there might be some part of your wealth that is cash. You know, money in your pocket. But your wealth might also exist in other forms as well, right? You might have a savings account. You know, over here where some of your wealth is stored. You might have property. You know, you have no cash in your pocket, but you do own a car, for example. It could be an example of how you have personal wealth. And in many ways, your personal wealth is conserved if this is all you consider. There can be exchanges between cash and cash in your savings and then cash and property. Like you could use cash to buy property. Property now becomes part of your wealth. You could put some of your cash into savings. You'll have less money on you, but you know that money is elsewhere for you to go get. And then if you need to go get it, you can go into your savings account, retract that money, and then you have it back in your hand as cash. So this would be an example of a conserved system as well. The amount, your total amount of personal wealth, if this is it, is fixed and does not change. But it could change, right? Money could come into the system if, for example, you had a job, maybe you get a paycheck. That would be a way for your personal wealth to increase. Stuff comes into your system of personal wealth. Though, in the same vein, there's ways for your personal wealth to decrease. Perhaps you have bills that you have to pay. That might make your personal wealth decrease. There might be also other things you spend money on that you cannot get back. Like say you take a vacation. You might say that your quality of life has increased by taking the vacation. But in terms of your personal wealth, you can't take a vacation, you pay for it with cash, and then after the vacation, give the vacation back and get your cash back, for example. So once you spend the cash, in this case, it's gone. These would be examples of how your personal wealth changes overall. Right? Paychecks bring money in, bills take money out. Experiences might take money out as well. Your wealth overall can take many forms. It can transform in different ways. It can change by total amount. This would be an example where the system is not conserved. Your wealth is possible. It's possible for your wealth to change. Though again, notice how it changed. You had some fixed system, and yes, I'm using the physics words to motivate what's coming. You have this fixed system, and then things are happening to the system. You know, either maybe a paycheck pushing money into the system, bills pulling money out of the system. So this is the idea behind conservation. And what we will see is, well, one thing we'll want to ask is what are the rules for when a quantity like, say, energy is or is not conserved? So let me write down what we will ultimately find as the answer, just so that we know what we're working towards. So we will find with energy that there's this thing we can define called the system. And there's a certain kind of energy which we call kinetic energy. And that is, in a sense, the cash of the system. Kinetic energy is energy that is associated with motion. But your system can also have savings accounts. and that is called potential energy. These are savings accounts where kinetic energy and potential energy can be exchanged with one another. I can turn motion into this, into savings. I can also cash in my savings and get motion out as a result. But overall, if I ask how much energy is here and how much energy is here, their sum always adds up to the same amount. The total energy stays the same, even though sometimes it might be lots of kinetic, very little potential, vice versa, evenly split, whatever you want. But then we will learn that the total energy of the system can change. If there's this thing called, we're going to call work, if something does work on the system, we will see that as a way for energy to be injected into the system, so that the overall total energy increases if work is done on the system. And then there is a way for energy to leave the system, energy that becomes lost, that we cannot get back. So we will see this as work done by what we will call non-conservative forces. Forces that are not very good at conserving energy. Friction is a great example of a non-conservative force. You cannot use friction to slow something down, and once that object slows down, you cannot get it back from friction. Friction has taken energy away from the system, and you can no longer access it. Thermal energy is a great example. Rubbing your hands together, there is motion in your hands. There are forces that are causing your hands to move, and you feel your hands warming up. That thermal energy, or the heat you're feeling coming off your hands, is energy that's being lost. It's drifting away, it's heating up the air in this room, for example. That would be an example of a non-conservative force. And then there's also another one where work can be done by the system on the environment. But we really will not ever see that, at least in this class. That's more of a stat mech or physical chemistry issue. So the takeaway here is that when we talk about conservation, it's really nothing more than an accounting problem. As long as you can take into account how much kinetic, how much potential, and then how things are coming in and out of the system, as long as you keep an account of all of that accurately, then you can apply the conservation of energy rules. Conservation of energy, or lack thereof, is nothing more than accounting for this next chapter. All right. What time am I at? Good. So that is where we are going. To get there, we have to define some new terms. We also have to upgrade our ability to deal with vectors. Particularly, we need to learn how to multiply two vectors. We've done how to add vectors. We can subtract vectors. We can multiply vectors by a constant. But what if I have two vectors and I want to multiply two vectors together? What does that look like? And why is that meaningful? I've motivated this or teased this a couple times. Suppose you have some axis and you have some vector v, say. We have already talked about, and you're probably now getting sick of hearing me talk about, how I can take this vector and I can break it into components. I can say that there is a component vx, and there's a component Vy, if this is the y in the x direction. And if I know what this angle is, right, I know, for example, that Vx is the magnitude of V times cosine of theta in this case. Vy is the magnitude of V times sine of theta. If the axis is at some weird angle, or maybe this is x and this is y, and there's some vector here which I will call v, that makes some angle. There nonetheless is a component that points in this direction, I might call it vx, and there's a component that points along the y direction, I'll call it vy. In this case, actually, the way I've defined it, Vx would still be V cosine theta, and Vy would still be V sine theta. So now let's think of this in terms of vectors. If I think of the axes, I can think of that x-axis and the y-axis. I can think of them as two vectors themselves. And we actually have already written down what those vectors are. When I write down a coordinate axis like this, those are lines that are pointing in a particular direction. For the ijk notation, we called that the I direction and the j direction. This was a vector that was 1, 0. This was a vector that was 0, 1. Those were vectors that told us the directions, what's going on in the x direction and in the y direction. And when I have a vector like this that has some angle, when I wrote down v sub x, or when I wrote down here v sub y, what I was doing is I was asking the question, all right, here are these two vectors I and j, and here's my third vector v. How much of that velocity vector, or v vector v, how much of it points in the horizontal or I direction, and how much of it points in the vertical j direction? And then we figured out that there was part of it points horizontal, v cosine theta, part of it pointed vertically, v sine theta, and those gave us the components that pointed in the same direction as the I vector and the same direction as the j vector. What if I had a more general vector here? Perhaps I have some vector w and I have some vector v. They're not exactly parallel to one another. They're not anti-parallel. They're not perpendicular. But I could still ask myself, how much is v pointing in the same direction as w? So I might do the same sort of thing. I could say, okay, this is the part that is like v along w. And then this part here is v perpendicular to w. This is not really a vector. So again, for an arbitrary two vectors, you could ask the same question. How much does v point in the same direction as w? How much does v point perpendicular to w? You might, this can be useful. We essentially saw this with ramps. We were doing the same sort of thing with ramps, where you had some box and gravity pointed down. And what you ultimately asked yourself was, how much of gravity points into the ramp and how much of gravity points along the ramp? And then if we knew the angle of the ramp, we were able to find those two components. Now let's formalize this and actually make it more general. Because in the case of v and w, you might think, oh, well, I see the triangle. Here's the triangle. So if I know theta, then I'm off and running. I can totally find what the lengths of those two sides are. And that's essentially generally what we are going to want to do. But there's a more general way we can do that. So define the dot product of two vectors, let's say A and B, where A might be there's some x component and there's some y component, and B where there's some x component and some y component. Oh dear, I've lost my screen. There we go. Move that back into view. Great. Admittedly, I'm sorry, I don't know when the screen died. So I'll keep this up just in case. Again, we're trying to find a more general way to find how much does a vector point in the same direction as another vector. This will be very important when we define work and how forces cause motion. So suppose I have two vectors A and B. I'm just going to do it for 2 dimensions right now. So there's an x and a y component for A. There's an x and a y component for B. The dot product between the two vectors is defined as A dot B. And the approach is you take the x components and multiply them together. And then you add to that the y component. You multiply the y components and you add them together. So in this case, it's ax bx plus ay by. If this was a third 3-dimensional vector, there would be then a plus az bz. If this was a 4-dimensional vector, there might then be a plus aw bw or whatever. So essentially, you take all the first coordinates, multiply them, the second coordinates, multiply them, dot dot dot, and then you add them all up together. Now this might seem ridiculous and just completely out of nowhere. But if we make this definition, the dot product actually has a lot of useful properties. And there's another way that this dot product can be written that proves to be more useful. But this is sometimes taken as the mathematical definition. Notice what you get as a result. This is a scalar, not a vector. The dot product, you give it a vector A and B, it gives you back a number. For example, if A is 1, 2, and B is 3, 4, then A dot B, those are 2 vectors, and I'm taking their dot product, would be 1 times 3 plus 2 times 4, that is 3 plus 8, that is 11. So the dot product of 2 vectors gave me back a single number, in this case 11. And the dot product has a lot of useful properties. The nice thing about the dot product is it kind of looks like multiplication. And the good news is that it obeys a lot of the same properties as multiplication. For example, A dot B is the same as B dot A. The order does not matter, like multiplication. The dot product distributes. If you have A dot B plus C, that is the same thing as the dot product of A with B plus the dot product of A with C. And you should convince yourself of this. It's easy enough to show a couple examples or prove, if that's your thing, with kind of 2 and 3D vectors. Let's see, if I have given a scalar alpha, I could have alpha, and then I could have A times B, or A dot B. There I could take the dot product, that gives me a number, then I multiply that number by alpha. The scalar multiple distributes, so that's also the same thing as take alpha, multiply by A, that gives me a new vector, then take the dot product with B. Versus, say, something like this. Scalars distribute through the multiplication sign. Just how, like, 1 times 2 times 3, I can move the 1 into different spots. That is the same thing as 2 times 1 times 3, or 2 times 3 times 1 in that case. Similarly, I assume you've done derivatives now at this point, so I can feel safe that everyone is okay with derivatives. The derivative of the dot product, you might think there was a product rule for derivatives, and that had a certain form. And indeed, the same rule holds in this case as well. The derivative distributes across the dot product via the product rule, like what you learned with derivatives in calculus. All right, now let's look a little bit more into the geometry behind the dot product. Let's go back to our previous example where I had the I direction and the j direction. I had some vector, let me call it v, and maybe this is 3, 2. Okay. You could calculate, say, how much the vector points in the horizontal or the I direction and how much it points in the j direction. You would find, of course, this length is 3 and this length is 2. Because that vector is the same thing as going to the right 3 and up 2. Which is why we wrote this sometimes as 3i plus 2j. Where I, to remember, is something like 1, 0. J, in this case, is 0, 1. Not sure why everything's red. Now let's take v dot I. That's the same thing as 3, 2 dotted with 1, 0. Remember, that is, I take the first components, 3 times 1, then I add to it the second components, 2 times 0, which is just 3. Okay. What about with j? This again would be 3 times 0 plus now 2 times 1. So the answer would be 2. Notice this 2 here is what we got from this dot product. Notice this 3 here is what we got from this dot product. And if there was a third dimension, it would also give you the third coordinate back. By taking the dot product with I, j, or k, or how many there are, these unit vectors, we're getting the component of the vector that points along that, of the vector that points in that direction. Dotting j with I, dotting v with I gave me the part of v that points in the I direction. Dotting v with j gave me the part of the vector that points in the y direction, or the j direction. Remember, we could have written this a different way as well. If we go back up to this image, we've identified that there's a triangle here. So we could have also written, for example, this component here which has a value of 3, is also the same thing as v cosine theta for whatever this theta is. This component here is the same thing as v sine theta for whatever sine is. And they would, of course, give the same answer. You can calculate the magnitude, you can calculate that angle. When you do v cosine theta, you get 3. You can calculate the magnitude, you can calculate the angle, you can do v sine of that angle, you would get back 2. Okay. Now let's see. Well, actually now what we're going to see is that this result is true in general. I'll write down the answer and then I'll prove it. I dotted, or A dotted with B, is the same thing as the component of A that points along B and then is also multiplied by the magnitude of B. Since A dot B is the same as B dot A, this is also the same thing as the component of B that points along A, multiplied by the magnitude of A. So for two vectors, A and B, so here's vector A, here's vector B, there is some component here where B kind of points, I might call this B parallel to A, which if we knew this angle would of course be the magnitude of B times cosine of theta. But maybe we don't know that angle. Maybe that's not given to us. What this is saying is that A dot B is giving us that parallel component multiplied by the magnitude of A. Or similarly, let me redraw. See if I can redraw it exactly the same. Yeah, not really. Or B, this is A. There is a part of A that points along B. I might call this A parallel to B, where A dot B gives me that parallel part multiplied by the magnitude of B. So the dot product is a way of, I like to think of it as the projection product. It is a way of getting the projection of one vector onto the other. How much is vector A pointing in the same direction as B? And we can do we can do a proof that gives us the more useful form of this expression, and then we're done. So take two vectors A and B. There's vector A, there's vector B. And then if you think back, this vector is then A minus B. Points to A from B. That's how I always remember it. And this forms some arbitrary triangle that is, in this case, kind of drew it as a right triangle, which I did not mean to do. I want to make it perfectly clear that this is not a right triangle. So I'm going to go extreme. So then this is A minus B. So there's no right angles anywhere to be seen here. Now there could be. This proof still works, but I don't want to assume. You may recall from geometry. I'm so used to drawing right triangles. I just draw them naturally these days. Here, how's this? For some arbitrary triangle that has some angle with various lengths, you cannot use the Pythagorean theorem to relate the lengths to one another, but you can use the law of cosines. Which, if this is theta, this is A, this is B, this is C. Remember that the law of cosine says that c squared equals a squared plus b squared. Looks like the Pythagorean theorem, but then remember there's the correction term. Which, if this were a right triangle, cosine of 90 degrees is 0, this just becomes the Pythagorean theorem. Law of cosines really is a more general relationship, where the Pythagorean theorem is just an example of it. But we can use the law of cosines now in the triangle I drew on the left. By the law of cosines, the length of one side, A, squared, plus the length of the other side, B, squared, minus 2 times the length of A, the length of B, cosine theta, equals the length of the other side of the triangle, which in this case is A minus B, squared. Pause and convince yourself that's true. All right, magnitudes are just lengths, so what I'm really just doing here is I'm just saying the length of A of one side plus the length, I'm using the lengths of the triangles, though they just happen to also be vectors. All right. We need one more relationship. So we need a quick aside. Take some vector c and dot it with itself. What do you get? Maybe c was cx, comma, cy. So I dot it with itself, cx, comma, cy. That is the same thing as the first component squared plus the second component squared. Notice that looks almost like the magnitude of the vector. The magnitude is the square root of cx squared plus cy squared. So that actually is a general relationship. The dot product with itself is just the square of the magnitude. Some textbooks actually use this as the definition of magnitude. Take a vector, dot it with itself, take the square root overall, that's the magnitude of the vector. And again, it's nothing new. It's just the Pythagorean theorem. But now I'm just writing it using vectors. All right, so we're going to need this later, so I'll highlight it so we remember it. So now if I look at, say, a minus b squared, and use the relationship I just wrote down, that is the same thing as the vector a minus b dotted with itself. We've convinced ourselves above, or you've taken for granted, or trusted me, that the dot product distributes, so I could do FOIL or whatever you want to call it. Oops, not a minus sign. So this is the same thing as, first, outer, inner, last. That's what FOIL means, right? It's been a while. And we can simplify this. A dotted with itself, we just said is the magnitude squared. B dotted with itself is just the magnitude squared. These two terms in the middle are the same, right? Because A dot B is the same as B dot A. So then this is just minus 2. Now write A dot B. And now see where you might see what's going to happen. So this thing in red is what you set. Let's see. So this right here is this. We just calculated what the magnitude of A minus B is, but that's also in our law of cosines. So the law of cosines is saying A squared B squared minus 2A B cosine theta equals the magnitude of A minus B squared, but we just show that that's A squared plus B squared minus 2A dotted with B. What joy. There's an A squared on both sides. I could subtract that away. There's a B squared on both sides. I could subtract that away. That leaves me with minus 2A B cosine theta equals minus 2A dot B. Minus 2's be gone. And we get our final relationship. The dot product is also the same thing as the magnitude of A times the magnitude of B times cosine of theta. That deserves a highlight. So now we've written down two different ways to calculate the dot product. I could take all the first components, multiply them, add that to the product of the second components, etc. Or I could also use this to evaluate the dot product. This is the same exact thing. It will give me the same exact answer. But notice, and then I will be done, this is exactly the geometric claim I was making. You have some vectors A and B. We said that B lies along A by some amount. This might be B parallel to A. But given this triangle, where this is some angle theta, B parallel to A is just the magnitude of B times cosine theta, which, notice, appears right here. So the definitions that I gave above still hold. The dot product gives you the component of one of the vectors that lies along the other multiplied by the magnitude of that vector A. Similarly, this dot product gives me the part of the vector A that lies along the vector B multiplied by the magnitude of the vector B. So this is useful because this is what allows us to connect geometrically when we talk about whether forces are parallel or perpendicular. You should convince yourself that, and I'll do this as a think about this for the next lecture. When two vectors are parallel to one another, what can you say about their dot product? When two vectors are perpendicular to one another, what can you say about their dot product? And this is something, again, like I had given you a link to a vector website before, and I said stop when you get to the dot product. Now go back, use that as another reference to learn about how a math class might describe the dot product, if that's helpful. All right, very good.